In this video, we'll derive the equations of motion using two techniques. One is using graphs and the other uses calculus. And we'll also find the relationship between work done on an object and its change in energy. Okay. We'll use calculus principles for that. Here we assume that the acceleration of the object is constant. So if you look at the velocity versus time chart, okay, the velocity is increasing linearly. Okay. So now assume that at the very beginning it's the velocity is u, okay, beginning of the measurement the velocity is u, and at the end of the measurement the velocity is v, and a time period of t has passed between these two measurements. So here the acceleration is constant. So you can write a equals v minus u divided by t. So this will immediately give us, if you rearrange the terms, a times t equals v minus u, or if you rewrite it as v equals u plus at. Okay, so that's the very first of the equations. Okay. Now, if you want to find the distance traveled, we find the area of this quadrilateral, which is a trapezoid. Okay. This side is parallel to this side. Okay. So in this particular case, the distance traveled is denoted by s. S is the distance traveled, is half the length of the two sides, the sum of the length of two sides, right, is half u plus v divided, and then we multiply that by the total time taken. Okay, so times t, and we know that v equals u plus at. So we plug this in here, so we get half u plus at times t. Okay, and so you write this as half of 2u plus at times t equals ut plus half at square. Okay, so that's equation number 2. Right. So now we want to find the third equation. Okay. So what we can see here is that the time taken, okay, the time taken can be rewritten here from here equals v minus u divided by a. And so if we take this particular expression and plug that in equation 2, right, so we get s equals u times v minus u divided by a plus half, okay, a times v minus u square by a square. So essentially this a and one of these a's cancel out, right? So, and here we get s equals u times v minus u divided by a plus v minus u square divided by 2a. Okay. Now we multiply both sides by a. Okay. So we get a times s equals u times v minus u plus v minus u divided by 2, and there's a square term here. Okay. So we collect the terms of v minus u on the right. We get u plus v minus u divided by 2, and therefore we get as equals v minus u times v plus u divided by 2. So we multiply by 2 on both sides. 2as equals v minus u times v plus u. This is v square minus u square. Therefore, we end up with v square minus u square equals 2as. Okay, or v square equals u square plus 2 times a times s. Okay, so that's the equation number 3. Okay, so these are the 3 equations of motion. So let me write that out. Okay, so the first equation was v equals u plus at. Okay. The second equation is s equals ut plus half at square, and the third equation is v square equals u square plus 2as, okay, where s is the distance. So these are the 3 equations. Now let us see if we can compute this using calculus. Okay, so we will try to compute these expressions, these very same equations, using calculus. Okay. So now we know that, okay, so let me push this out of the way. We know that dx or dt, okay, is v, okay, because that's the definition of velocity, and d2x divided by dt square is the acceleration. We know that. Okay, so d2x or dt square can be written as d or dt, dx or dt, okay, equals a, or we can write this as d or dt of v equals a. Okay, so the change of velocity with respect to time is the acceleration. Okay. So now we can use chain rule. So we can use dv or dx times dx or dt equals a, essentially, because the dx's will cancel out and we get dv or dt. Okay, so and we know that dx or dt is nothing but v, so we can write this expression as v dv or dx equals a. Okay, so these are the 2 ways of representing acceleration. Okay, one is this way, the other is this way. So let's take the second method and we'll try to use that for our purposes. Okay, so we have v dv or dx equals a, and so we multiply by dx on both sides. So we have v dv equals a dx, and then we integrate, okay, and we add a constant to that, okay, when we do that. So what we see here is the left side becomes v square divided by 2 equals a times x, okay, plus c, okay, where x is the distance traveled. Okay, now when x is 0, okay, that is at 0 time, the velocity is the initial velocity. Okay, so we end up with a constant term equal to u square divided by 2. So we plug that constant term into this equation. So we get v square divided by 2 equals a times x plus u square divided by 2. We multiply by 2 on both sides. We get v square equals u square plus 2ax. And in our previous expression, we used s instead of x, so we actually can rewrite this as u square plus 2 times a times s. So that's the pretty much the first equation that we got from here. Okay, so let's look at another equation to derive, and here we know that dv or dt equals a. Okay, so we multiply by dt on both sides. dv equals a times dt, and we integrate. We add a constant to the right. So we have V equals AT plus C. So at t equals 0, V equals U. Therefore, the constant term equals U. Therefore, V equals U plus A times T. Okay, so that's a very interesting observation, right? Okay, so we have derived the second of the equations. So let's derive the third one. Okay? So now here, so we know that V equals U plus AT. So we write V as dx over dt equals U plus AT. So we multiply both sides by dt, we get dx equals U plus AT times dt, and we integrate, we add a constant term. Okay, so let me write this better. Okay. So therefore x equals here integration u dt plus a times t dt plus c equals ut plus half at square plus constant. Okay, so now when t is 0, the distance traveled is 0, therefore the constant term is 0, right? So x here equals ut plus half at square. In our previous derivation, we had used x equal to s. Okay, we had used s instead of x, so we have s equals ut plus half at square. So what we've seen here is that we have these expressions. Okay, so we have derived the very same expressions, here, here, and here using calculus. Okay, so you can use any method you want. So now let's use calculus again to find the relationship between work and energy. Okay. So, so we know that the work energy theorem tells us that the work done equals to the change in kinetic energy, and that's what we will prove. Okay, so if you look at the work done by an external force, so the force here equals mass times acceleration, right? So now the work done here due to this force equals F times dx, right? And where F is the instantaneous value of the force. To find the total work done, we need to integrate, right? So we know that the acceleration is dv or dt, and so we rewrite this using the chain rule as dv or dx and dx or dt, okay, is v dv or dx. Okay, that's what we have seen before. So we take this and plug it in, okay, into this expression. So what happens in this case is that the work done equals m times a is v dv or dx times dx. Okay, so we can effectively cancel out the dx's here for our purposes, and therefore the work done equals mv dv, right? And this integral has two limits. You start with an initial velocity and end up with a final velocity. This is half m v square between u and v, so equals half m v square minus half mu square. So that's the work done. Okay, and we see that this is the kinetic energy in the end state, and this is the kinetic energy in the initial state. So this is nothing but delta Ke. Okay, so the work done is equal to the change in kinetic energy. So we know that. Okay. So now here is that if this is a conservative system, right? If this is a conservative system, then the total energy is constant. Okay, in a conservative system. Okay, so now what we do here is we write the expression for energy as the sum of kinetic energy and the potential energy. So if energy is constant, then change in energy equals the change in the kinetic energy plus change in the potential energy is actually zero, right? So the change in potential energy equals minus the change in the kinetic energy in such a case. Okay, and this, remember, holds good only for conservative systems where there is no dissipation. So the change in the potential energy here will be equal to the negative of the work done. Okay, so here we have looked at some calculus ideas. We have looked at some graph based ideas to derive some equations, right? So to recap, so we computed the equations of motion using graphical means, right? And we computed the equations of motion using calculus here. Okay, and now we used calculus to compute the relationship between the work and the change in kinetic energy, and related that to the change in the potential energy of the system. Okay, so I hope this gives you an idea of the calculus based underpinnings of physics, and it will encourage you to think about the mathematics behind physics in future. If you like this video, please click on the like button and subscribe to this channel so that you can get further updates. Thank you.